So today in our 1.4 video, we finally get to talk about derivatives. So 1.4 is all about what is a derivative and how do we calculate derivatives. Well, derivatives are related to rates of change. So I wanted to revisit this unemployment rate graph that we talked about last time. Okay, last time we found the average rate of change from 1975 to 2014, right? We found that it was about negative 0.0564% per year. So over the past 39 years, the unemployment rate's gone down by about this much per year. But that's not reflective of what's happening each year. You'll notice that the unemployment has fluctuated over the course of these 39 years. In fact, let's look at the year 2008. Oopsies. 2008, the USA went through a recession, and so you'll notice on the graph, okay, here's 2008, the unemployment's starting to spike. It's not going down, the unemployment's skyrocketing. So this average rate of change doesn't actually reflect what's happening in 2008. So what if I was wondering, well, how is the unemployment changing in 2008? What if I asked that question? Employment rate changing in 2008. Another way I could say that is, what's the rate of change in 2008? Okay. Well, in order to figure that out, I don't want to use my big interval. I don't want to use my 39-year interval. I want to pick an interval that more accurately represents what's happening in 2008. So I could pick an interval like 2007 to 2009. That still includes 2008. But what I've done is I've shrunk that interval down a lot smaller. Okay? To where now my change in years is only 2. Okay? And so then I could calculate my average rate of change, right? I could do change, so change in Y over change in X. My change in X is just 2009 minus 2007. In 2009, my unemployment's about 9.3%. And in 2007, my unemployment's about 4.6%. Okay. This leaves me with, I get about 4.7% over 2, which is 2.35% per year. Okay. So, around 2008, the unemployment rate was actually going up by about 2.35% a year, which is much different than my average rate of change over the whole 39 years. And how did I get that? I got that by decreasing the size of my interval right about where I'm concerned. Now, this is still, to be clear, this is still an approximation because I'm using values from 2007 and 2009 to help me with what's happening in 2008. Okay? To get more accurate, I'd have to decrease the size of my interval even more, but I'm reaching the limits of what's possible with my graph because my graph only has specific data points. If I have a function though, or if I have an equation, I can plug whatever numbers I want in, and I could theoretically get this interval as small as I want. I could use an interval the size of 0.01. I could use the interval size of 0.001. Okay? So, this begs the question is, can I get an infinitely small interval? Because like we said, the smaller the interval, the more accurate the rate of change is going to be for a specific point. So can I get an infinitely small interval? Well, it turns out I can't with this data, of course, because it only has specific data points, but with an equation, I can. If I have an equation, it's possible, okay? We call this a derivative, okay? Derivative, okay? What a derivative is what's called an instantaneous rate of change. It's the rate of change at a specific point, okay? And that's what a derivative is, okay? And like I said, if we have an equation, it's possible to actually calculate this. How do we do it? Well, let's revisit the difference quotient, okay? So just as a reminder, my difference quotient is this whole f of x plus h minus f of x over h, where x is your starting value, where you're going to start finding your average rate of change, and h represents your interval size. Or you could also think about it as your delta x, right? Your change in x, your interval size. Well, if I'm looking for the instantaneous rate of change, then I want that interval size to get as small as possible, okay? Well, we can't actually let the interval size reach 0 because then I have a discontinuity. But what I can do is I can take the limit as h approaches 0. Using that limit, I can solve for this. And this gives me the, this gives me the derivative at x. If we're using function notation, the function notation for a derivative is, oh, that was kind of squiggly, a little apostrophe. We call this f prime of x. If we're not using function notation, then you'll also see derivatives written like this, dy over dx, okay? And you might be wondering where that notation comes from. Well, that notation is pretty simple to explain. Remember, with average rate of change, we use delta y over delta x, where delta represented just any change. Well, this lowercase d just represents an infinitely small, that's spelled wrong, small change. And then in that case, that's the same notation as just your average rate of change, which once again, that's what a derivative is. It's an instantaneous rate of change. Okay. So let's try this out with a function, okay? Let's see if we can find the derivative for a function. So let's take a look at, let's have a function. I'll give you a function. The function is 4x minus 3x squared, and I want to find the derivative at x equals 2. Okay? Remember, by derivative, what am I talking about? I'm talking about this instantaneous rate of change. That's what a derivative is, this instantaneous rate of change. Okay, so once again, the key to this is using the difference quotient. Okay, I'm going to take the limit as h approaches 0 of my function, f of, in this case, what's my starting value? Well, since I'm finding the derivative at x equals 2, instead of x, I'm going to put in 2 plus h minus f of 2 over h. Okay, let's see what we get. Okay, f of 2, to figure that out, all I'm going to do is just plug 2 into my function. So f of 2 is just 4 times 2 minus 3 times 2 squared. I get 8 minus 12, right? 3 times 4 is 12, and so f of 2 is just equal to negative 4. Okay. F of 2h, though, I have to kind of write out. So I get 4 of 2 plus h, 4 times 2 plus h, minus 3 times 2 plus h squared. That's my f of 2 plus h minus f of 2, which we just saw was negative 4, all over h. Okay, so let's expand this out. When I distribute, I get 8 plus 4h minus 2 plus h squared. I have to do a little bit of foiling for that one. I get 4 plus 4h plus h squared. And then minus negative 4 is just a plus 4 over h. Now I got to distribute this negative 3. I get 8 plus 4h minus 12 minus 12h minus 3h squared plus 4. Okay. Well, like we saw yesterday, when I'm doing difference quotients, a lot of the times what will happen is things will cancel out so that I can get rid of the h in the denominator. Notice 8 minus 12 plus 4 gives me 0. So that cancels out all of my constants. Oopsies. And now I'm left with 4h minus 12h minus 3h squared. Every term in the numerator has an h in it, which means I can factor out an h. Once I factor out this h, it can cancel with the h that's on bottom, and I'm left with 4 minus 12 is negative 8 minus 3h. Okay, so I was able to simplify that pretty well, and what am I left with? I'm left with the limit as h approaches 0 of this new function. I no longer have a discontinuity at h equals 0. Which means, to find this limit, all I have to do is just plug in 0. Well, if I plug in 0, negative 8 minus 3 times 0 is just 0, and I'm left with negative 8. So, that represents the instantaneous rate of change of my function at 2. Okay? Even though... and what that means is that's if I let my interval become 0. I was still able to find a rate of change. In fact, let's take a look at what the graphs look like. So this is my graph of 4x minus 3x squared. That's what my graph looks like. And remember, we were finding the derivative, or the instantaneous rate of change, at this point, at x equals 2, and the corresponding y value is negative 4. Okay? Well, look what happens when I actually, look what happens when I actually zoom in at this point. That's what this represents. If I zoom in at this point, x equals 2, y equals negative 4. And you notice, take a look at the scales. You'll notice I zoomed in quite a bit. If I zoom in, my graph looks linear. And if I look at the slope of this quote-unquote linear line, even though it's not linear, it just looks linear because I've zoomed in so much. If I look at this slope, I'm going down 1, 2, 3, 4, 5, 6, 7, 8, and over 1. A slope of negative 8. Which is exactly what we found right here for my average rate of change, or for my instantaneous rate of change. So that's what a derivative is. The derivative is the instantaneous rate of change at a point. Okay? Well, it turns out we can actually find derivatives of functions without actually knowing what x value we're doing this out. So I'm going to come back up here and I'm going to say, I'll go over here. What if we find the derivative of 4x minus 3x squared And I'm not going to specify where. I'm just say find the derivative of this function. Okay. Well, I'm still going to use the difference quotient. But in this case, since I don't have a specific x value, I'm just going to leave it as x. And I'll go from there. See what happens. Okay? This gives me 4 times x plus h minus 3 times x plus h squared minus 4x minus 3x squared. Okay? I'll go ahead and multiply everything out and take a look at what happens. Okay? I get 4x plus 4h minus 3x squared minus 6xh minus 3h squared minus 4x plus 3x squared. Sorry, I was squishing myself over there. I didn't realize I could scroll over more. Okay, this looks pretty crazy, but if I take a closer look, 4x minus 4x. Negative 3x squared plus 3x squared. Once again, the terms that don't have an h in it end up canceling out. And so I'm left with 4h minus 6xh minus 3h squared all over h. All of those terms in the numerator have an h in it, so I can factor out the h. Oopsies. And I have 4 minus 6x minus 3h all over h. Those h's now cancel because I was able to factor out an h out of the top. And I'm left with the limit as h approaches 0 of 4 minus 6x minus 3h. If I let h approach 0, all I'm left with is 4 minus 6x. And this right here represents the derivative of the function. Now, once again, I didn't specify an x value. So what this allows me to do, this actually ends up being really, really helpful, because what that allows me to do is I can now find the instantaneous rate of change at any x value by using this simple formula. If I want the instantaneous rate of change at 0, I can just plug in 0. And in this case, my instantaneous rate of change would be 4. My function's going up 4 over 1 at 0. If I want my instantaneous rate of change at 2, or we already found that one, at 1, I could just plug in 1. See what I get? Okay. So that's how we can find derivatives of functions without actually knowing what the x value is, or without having a specific x value. Okay. So there's quite a few problems on your homework where you're finding the derivative at a specific point. You're welcome to pause this video, work on some of those. There's also a few questions on your homework where you're finding the derivatives of just any function without specifying an x value. So you're welcome to pause the video and also work on a few of those. But the last thing I want to talk about is our tangent lines. Okay, and so to do that, I want to come back to these pictures of my graph that we looked at earlier. Okay. Hopefully you guys may have heard of tangent lines before. You've at least heard of the phrase going off on a tangent. Okay, and that phrase comes from this idea of tangent lines. So what a tangent line is like we saw, if I zoom in at this point, I get something that looks linear. So if I zoom back out and come over here and say, well, what if I were to draw my approximate linear line right here? Okay. I'm drawing a picture of that linear line that matches the what the graph is doing at that point. Well, that begs the question is, what's the equation of that linear line? Okay. So let's see if we can figure out what the equation would be for this line. Okay. Well, Oopsies. To find, normally to find the equation of a linear line, I want to put it in slope-intercept form, so I'm looking for the slope, and I'm looking for the y-intercept. What's the slope of this line? Well, it turns out the slope of this line is the instantaneous rate of change. So my slope is equal to the derivative at the point that you're looking at. In our case, it's the derivative at 2. Okay? So we already figured that out. We figured out that the derivative at 2 was -8. So this leaves me with y equals -8x plus b. Well, what's my y-intercept? You'll notice with what I've drawn so far, I haven't crossed the y-axis yet, so I don't know the y-intercept of my green line. Can I just use the y-intercept of my function? Well, no, because what that will do is that'll move the function over here. And I don't want the function over here. I want the function going through the point that we're looking at. So this means that I need to actually figure out what the y-intercept is. Or I can use point-slope form. So if you remember, point-slope form is this form y minus y1 equals m times x minus x1, where x1, y1 is a coordinate point that you know the line goes through. Okay? In our case, this coordinate point that I know the line goes through is the point where I'm finding the derivative. In our case, 2, -4. So using point-slope form, I can get this equation fairly quickly. Y minus -4 equals my slope, -8, times x minus 2. And so I get y plus 4 equals -8x plus 16, and then I can solve for y, and I get -8x plus 12. And that's my equation for my tangent line. These tangent lines actually become very helpful if I'm ever approximating values. It's used for Newton's method. I don't know if you guys have heard of that, which is used in a lot of number theory or computations, a lot of advanced computations that computers do. It uses this idea of a tangent line. Okay, so to sum up a tangent line. Okay, so to find the equation of a tangent line, you just use point-slope formula. Okay, or I guess, and with tangent lines, we'll always give you a specific x value. Okay, so let's say x value of just an arbitrary value of c. Then you'll do y minus, well, your y value is just whatever your function value is at c, equals, your slope is the derivative at c, or the instantaneous rate of change at c, times x minus. And that's your equation. And that's how you can find the equation of a tangent line. Okay, good luck on the assignment as you work on it. Once again, feel free to reach out and ask questions if you have any. Thanks, guys.